Good morning, students. We started with rotational dynamics. Already we have covered some part of it. So we will continue with the same. We have started with banking of flows. Now banking is a process in which the outer edge of the road is raised above the inner edge in order to make the speed of the vehicle independent of the friction, force of friction. We derive two formulae. I'll write the formula and explain. V max or V optimum, you can say. The value of this we want to be root Rg tan theta. This derivation already we have done. In this we said the exact speed with which the vehicle should travel on a curved horizontal road is root Rg tan theta. A bank road is root Rg tan theta. Then in the last lecture we derived an expression for minimum speed on a curved bank road that came out to be root Rg into bracket tan theta minus mu upon 1 plus mu tan theta.
Sir, just 1 second.
Now we want to derive what is the maximum speed of the vehicle on a curved bank road. Assume that this is the road which has a curve towards the left and the vehicle is traveling on this. The optimum speed, that is the exact speed with which the vehicle should travel, is given by this. The minimum speed with which it should travel is given by this formula. If the speed of the vehicle decreases below this limit, this vehicle will start moving on this side towards the lower edge of the road. Now, if you increase the speed beyond a certain limit, the vehicle will travel towards the outer edge of the road. So, we want to know the minimum and the maximum speed of the vehicle on the curved track. So, we will start with this last derivation from this chapter, or rather this part, banking of roads. It is exactly similar to the previous derivation. I will explain what is the difference. So, we are going to find out maximum safety speed on a bank curved road. The question is worth 3 marks, many times asked in the board exam. In the previous syllabus, this was included. The previous derivation was not included. So, we will again consider all the forces acting on the vehicle. Assume that this is a road banked at angle theta. Means the road is making an angle theta with the horizontal. As I told you in previous derivations, the first force that you will consider acting on the vehicle is mg, that is the weight of the vehicle. The second force, it will be normal reaction denoted by letter n. This normal reaction we are going to resolve into two components. In the last derivation I explained to you, if you rotate this angle by 90 degree, this angle has to be theta again. These are equal. The component next to the vector is always cos theta component. The component which is opposite to the vector is always sin theta component. Now, assume that this n sin theta, which is going to provide the centripetal force for the circular motion, is greater than, if n sin theta is less than mv square upon r. if n sin theta component is less than the centrifugal force, which is mv square upon r, the vehicle will start moving in this direction. If such a thing happens, the force of friction, as we have discussed before, it is always opposite to the motion. If the vehicle starts moving this way, frictional force will be opposite to the motion. So this is F. This angle again comes out to be theta. If I resolve this, I will show the resolution once again separately. Then this is opposite side, it is n sin theta, and n cos f sin theta. F cos theta component will be towards the left. Now, how the resolution has been shown? Assume that this is vector n. So, this component has been shown as n cos theta. This component is shown as n sin theta. Second vector is this, which is force of friction. It is resolved as F cos theta, this is theta, and F sin theta. So what we have got is, if you combine these two, you combine this origin with this, then you are going to get this type of resolution. Now, what are the forces upwards n cos theta, downwards mg plus f sin theta? These two are going to nullify each other's effect because the vehicle is not moving up or down. It is in contact with the road. Therefore, I will write mg plus, these two forces are in the same direction. So, f sin theta equal to, what is the force in the upward direction? N cos theta. This is my, sorry, I will shift this on this side and then label it as 1. N cos theta minus f sin theta. This is equation number 1. What is going to happen next? Now, the forces which are in the horizontal direction, they should also be equal. Otherwise, vehicle will, if this force is greater, it will move on this side. If this force is greater, vehicle will move on this side. What is the force on the right hand side? It is centrifugal force mv square upon r. What is it equal to? It is equal to sum of the two vectors. The two vectors are n sin theta and f cos theta. N sin theta plus f cos theta. Recall the previous derivation. What we did? We divided second equation by the first one. In short, I am writing 2, equation number 2 divided by equation number 1 means what? Divide left hand side by left hand side. mv square upon r upon mg equal to, divide right hand side by right hand side, n sin theta plus f cos theta upon n cos theta minus f sin theta. What all things cancel? Here m will cancel. So what will be the next step? V square upon Rg. V square upon Rg equal to. Now I am skipping one step because in the previous derivation also we have done this. Divide each term in the numerator and denominator by n cos theta. So I am getting n sin theta upon n cos theta plus, what is here? F cos theta. F cos theta upon n cos theta. What I have done? I have divided the numerator by n cos theta. So same operation I have to do in the denominator. in order to maintain the value of this right hand side constant. So now I am dividing denominator each term n cos theta upon n cos theta minus f sin theta upon n cos theta. Now check which terms get cancelled. Here n gets cancelled. Here cos theta gets cancelled. Again repeating, you are not supposed to cut like this in the exam. It is for understanding purpose. Don't scratch it or cut it using pencil also. Don't do it. This n cos theta cancels out and here nothing cancels out. So what is the value of v square upon rg now? Check. Sin theta upon cos theta is tan theta plus here f upon n. What is the value in the denominator? This comes out to be 1 minus f upon n. Again sin theta upon cos theta is tan theta. Shift this rg on the other side. Rg into bracket tan theta plus mu upon 1 minus f upon n. Then in the next step we will substitute for that. Now again, what does first law of friction say? It says that force of friction equal to mu n. This is according to first law of friction. So from this I get f upon n to be equal to mu. So I have to substitute it here and here. So v square equal to rg tan theta. Instead of this f upon n mu 1 as it is minus sign f upon n is mu and theta. I want to find out value of v. So now just take the square root and label it as v max equal to square root of rg tan theta plus mu upon 1 minus mu tan theta. This is the expression where you have to land. So we have got three different formulas. One for optimum speed, one for minimum speed, one for maximum speed. Means if you are traveling in a car along a curved bank road, the value of your speed should be between V max and V min. Your speed should range between these two values. For V max you have this formula. For V minimum, what is the change? This becomes minus, this becomes plus. So remembering the formula is very easy. This is related to banking of roads. Now we will move to another 3-mark question, which already you have studied in the 11th standard, but it is again included in 12th standard syllabus. So we have to deal with it. It is related to conical pendulum. First we will define conical pendulum. What a pendulum is, ideal conical pendulum, and then move forward to find the periodic type of conical pendulum. All of you have seen a simple pendulum. It is nothing, I am drawing it on this side. It is nothing but a heavy point mass. You attach a metallic bob to a thread, allow it to spin or pull it on one side and release. So it will start traveling and it will continue moving like this. This is what is called as simple pendulum, and with the ideal simple pendulum we define as heavy point mass. Now sphere, if you consider, its center of mass is the center of the sphere, so that can be considered as heavy point mass, attached to a massless inextensible string. What we are talking about are the ideal condition. Now if you have a string, it will have mass. Any material particle has mass. So this cannot be massless. At the same time, we define it as inextensible. You take any string, even a wire, its length will also increase if you attach the load. This you have studied last year in chapter elasticity, properties of matter. So we cannot have ideally massless or inextensible string and hanging from a rigid support. So this part of the definition is same. What we are saying here, heavy point mass attached to an inextensible massless string hanging from a rigid support, carrying out oscillations in which plane? In the vertical plane. Now, for conical pendulum, the initial part is same. We are considering conical pendulum now. What does the word conical suggest? It suggests you should have a cone. So it is again a 3-mark question. Derive expression for periodic time of conical pendulum. First I am defining heavy point mass attached to a massless inextensible string hanging from a rigid support. How this was carrying out oscillations in the vertical plane. This carries out circular motion in the horizontal plane. It is going to carry out circular motion in the horizontal plane. Now during this motion, it traces out a cone. Observe this diagram. It appears like a cone. This is called as semi-vertical angle. Half the total vertical angle. We want to find out in how much time it will complete one rotation. And that will be called as periodic time. So for that, what we are supposed to do? We have to resolve the forces acting. First force, as always, weight of the particle. Now here there is no contact. It is not resting on a surface, so there will be no normal reaction. But instead of normal reaction, another force which tries to balance the weight is called as tension in the string. I am labeling it as capital F because we are going to use capital T for periodic time. So instead of using T for tension, I have used letter F as force. I want to resolve this into two components. See, this is theta again. You can easily understand parallel lines, transversal, alternate angles. So these two angles are common. What is the component next to the angle? It is always cos theta. So I am writing it as cos theta. What will be the direction of other component? It will be along the radius towards the center. So it is F sin theta. What are the terms used? Let R be the radius of the circle. This one. Let L be the length of this string and H be the height. Now, we want to find out periodic time. How periodic time is related to angular velocity? It is P equal to 2 pi upon omega. I will get value of T if I find out omega, and that I am going to find out from this particular diagram. It is very simple. The bomb is at a certain level, so upward force equal to downward. So if we find angular velocity, then we can find the periodic time. Now how to approach this? Up till now we were considering that centripetal or centrifugal force is mv square upon r. Now we will consider the centripetal force in terms of angular velocity. If you recall, we have done the derivations previously in which we said centripetal force equal to mv square upon r equal to mr omega square equal to mv omega. These were the minimum that you have to know. You can modify these in two other ways, but that we are not interested in now. I will consider this part as centripetal force. Now, how to approach? What you did in the previous derivation in banking of rods, you did balancing of forces. Now, this ball is neither moving up nor moving down. So, upward force must be equal to downward force. So, I get mg equal to F cos theta. This is the first equation. It is very simple derivation. Centripetal force F sin theta. Who is going to provide it? Centripetal force is provided by this component of tension. Tension is actually acting along the length of the string. You resolve this in two components. The component which is directed towards the center of the circle, that is going to provide centripetal force. So, now I am using mr omega square equal to F sin theta. From where it has come? It has come from the fact that the centripetal force being the real force, it has to be provided by one of the real forces. And in this case, the real force is the tension. So tension, component of tension is providing you this. What did we do in the previous derivation? Divide second equation by first. Almost all the equations or all the derivations in this chapter, we are following the same procedure. We are trying to balance the forces and we are trying to find the condition for equilibrium. That is what we are doing now. Now divide equation 2 by 1. Left hand side by left hand side. mr omega square upon mg equal to F sin theta upon F cos theta. What are cancels? M and F. R omega square upon G equal to tan theta. This is my equation number 3. Now, I want to find out tan theta by trigonometry method. If I consider this triangle O, this point as A and this point as B, in triangle OAB, now you were writing the derivations in geometry or proof in geometry. In triangle OAB, can you visualize what is tan theta? See, I have got value of tan theta by this balancing of forces. Now I want to find out tan theta from the trigonometric ratios. This is theta in this triangle. Tan theta is opposite side upon adjacent side, so I am writing directly as R upon H. This is my equation number 4. From equation 3 and 4, what you observe, one side of the equation is same, so other sides of the equation must be equal. So I will write from 3 and 4, that is equating equations 3 and 4. I will write R omega square upon G equal to R upon H. R gets cancelled, bring this G on this side. Omega square equal to G upon H. Omega equal to root G upon H. Now observe the first equation. You have already got value of omega. I am going to substitute that value in the first equation. So you will get periodic time T equal to 2 pi upon square root of G by H. When taken in the numerator, it will be 2 pi under root H upon G. Now in triangle OAB again, if you have the diagram, refer to it. What is cos theta? Observe, cos theta is h upon L, which implies h equal to L cos theta. Substitute this value here. The periodic time of conical pendulum comes out to be 2 pi under root L cos theta upon G. So observe the factors on which the periodic time of conical pendulum depends. It depends upon length of the spring. It depends upon what is the semi-vertical angle, and it depends upon the gravitational acceleration at that point where you are performing the experiment. This question is also worth 3 marks. So do it properly. Already you have done it well. In the next lecture, we will start with vertical circular motion. That is another type of motion here. Thank you.